Assalamu alaikum, guys. So let us give a small definition of a periodic or short definition of a periodic signal. So a periodic signal, what is a periodic signal? So a signal xt can be said as a periodic signal. So a signal xt is periodic with period t if xt signal is nothing but the xt plus kt. Okay, this is the condition for all t and all k. This is all symbol for all k. So basically, it means that if you take xt and shift it to your xt at any multiple of capital T, then the signal remains unchanged. That is xt is a periodic signal, right? So if any signal xt, if you change it to its period or any period or any integer number of period, then signal remains unchanged. That is called a periodic signal. For example, if we draw a periodic signal, this is the best very common example of a periodic signal is a sinusoid. For example, this one. Okay, so this can be write as a sine 2 pi ft, right? So here is a one period, right? This is one complete t up to this one cycle. So if this is on 1t, then this is actually 1 by f, because we know t equal to 1 by f. So in this case, this will be 1 by twice f. This will be 3 by twice f, right? Like this. So this will be twice by f, something like that. Okay, here. So this is actually an example of a periodic signal. Periodic signal. You see, if you change t, like this t, then from here to here, another t, right? So say, for example, this is first t, 1t, this is the second t, 2t. Actually, not the 2t, it's actually second t. This is not 2t, this is second t. So if you keep changing the number of integer number of t, the signal remains unchanged. So this portion of the signal is same as this portion of the signal will be also same as that portion of the signal, something like that. Okay, so that's a signal is called a periodic signal. This kind of signal is called a periodic signal. Here f is actually the 1 by t, or t equal to 1 by f. Okay, and this f is nothing but the fundamental period, or t is a fundamental period. Okay, so f is the fundamental frequency, t is the fundamental period. So here this t is the fundamental period, or this value is the fundamental period. Okay, so now let's say sine 2 pi f. Instead of t, what you take? T plus any integer number of period t, right? Okay, so what we find? Sine 2 pi f t plus 2 pi kft, right? Kft. Here you see f equal to 1 by t, means ft equal to 1, isn't it? If this is the case, then ft becomes 1. So this becomes sine 2 pi f t plus, so ft becomes 1, so 2 pi k. K is the integer. Okay, so you see, for any k, whatever the value of k, right? K could be 0 to some very large value, n value. For any value of k, what happens? You can see that is nothing but the sine twice by f, right? Twice by f t. Because the sign is shifting every time twice pi, right? For example, you are here, so this is pi, this is twice pi. So every time you are in twice pi, you are in twice pi, you are in the twice pi, you are in twice pi, right? So you are in the same value. So now we can see that this remains unchanged. The signal remains unchanged. Okay, so that's why this is called a periodic signal, where its value for any integer number of t, capital T, period, the value remains unchanged. Okay, so this is the definition of a periodic signal. Thank you. So we have just described a periodic signal. So let us know something about non-periodic signal. Okay, so non-periodic signal. So non-periodic signal is also called aperiodic signal. We like to know about, it's actually time signal or aperiodic continuous signal. We can say actually it's a aperiodic continuous. So one of the example is actually something like that, a pulse wave signal minus t by 2 to t by 2. This kind of is a aperiodic signal. Means actually it's not happening continuously, right? I mean, it's not happening in period. So let us say a time signal, signal xt. So let's say a aperiodic time signal, aperiodic. Let's say a aperiodic time signal xt. So what is this Fourier transform? So it's Fourier in this frequency domain representation. If you remember this lecture, here we say that the spectrum of a signal, means the frequency representation of a signal, is called a spectrum of a signal. Actually have a two different representation. One is the Fourier series and another is a Fourier transform. That part actually we will actually describe here. Okay, so the Fourier transform of this xt will be xf in the frequency domain. So it becomes capital X and capital F. This is how the Fourier transform is actually denoted. So this Fourier transform is denoted as, so its Fourier transform is XF. XF is nothing but minus infinity to plus infinity xt e to the power minus j 2 pi ft dt. This is how actually we express a Fourier transform. Okay, so here this part is a Fourier. So this is our actually Fourier transform, okay, of signal xt. Okay, and this is a complex sinusoid, right? This is actually a complex. So f is a frequency, and so this f actually is denoting that the signal is in frequency domain, and this signal t is denotes that is actually in time domain. So xt, signal xt, and signal in xf, they are actually there is a change of domain happens here. So this we actually also called it Fourier transform pair. So signal xt was a non it has a real value, but signal xf, it has a complex form, means real and imaginary part, both of the part is there, right? We know it from Euler's formula. So xf, so what we can write that xf if xf is in general, it's a complex. xf is still complex because of this one, because of this quantity. xf is in general a complex value, so xf can be, it has a both amplitude and phase, so or magnitude or phase. So if xs is expressed, it has a magnitude spectrum, it has a magnitude spectrum, means xf this spectrum has two, one is the magnitude and another one is its phase. So xf signal, because of its complex, it has a both magnitude spectrum and it has a phase spectrum. Now if we have a signal xf, we can actually reverse back to the xt. How? By doing if, inverse Fourier transform, by doing inverse Fourier transform. By doing inverse Fourier transform or IFT, we can actually bring back our frequency domain signal to its original time domain. Where if this xf is known, then xt is nothing but minus infinity to plus infinity x of f e to the power j2 pi ft dt. So there are two ways. This is if you do the inverse Fourier transform, then you take back the time domain signal from its frequency domain signal, and this is actually a Fourier transform where if a time domain signal is known, then its frequency domain signals can be, Fourier transform can be derived. Okay, thank you. So in continuation of Fourier transform, let us continue with the modulation property of the Fourier transform. So this topic is the modulation property. The modulation property of Fourier transform. Okay. Let's see what is the modulation property of the Fourier transform. Now we have already seen that a periodic signal or a signal xt can be expressed as a Fourier transform by multiplying with a complex sinusoid. Okay, so let us consider a signal xt, which will be modulated by a complex sinusoid e to the power j 2 pi ft, and the resulted signal is called modulated signal, which is given as a x tilde t. So this is modulated signal, TED signal. This is our original message signal, and this one is actually complex sinusoid. Is actually complex sinusoid, which is here this fc. So this fc is the carrier frequency. Or this complex sinusoid, this is also a carrier. This is actually a carrier signal. So we are saying that if you have a message signal, if you multiply with a carrier signal, you will end up with a modulated signal. So this complex sinusoid here and the carrier frequency fc has a very high frequency. So this is actually a fundamental concept that how a low frequency message signal can be multiplied by a high frequency complex sinusoid to have a modulated signal or high frequency signal. So here we can by Fourier transform that we have covered earlier, we can say that the xt, the Fourier transform will be xf, right? So what will be the x tilde t? This is so what will be the Fourier transform of this signal x tilde t? So the Fourier transform of it will be capital X tilde f. This is the notation. So what will be this value? So if we want to find it, x tilde f is nothing but the, how the frequency to time domain works, right? From this one, sorry, xf. This one. If you have a, how you find a frequency domain signal or Fourier transform from its time domain signal, okay? So xf, x tilde f is nothing but minus infinity to infinity x tilde t e to the power minus j 2 pi ft dt. This is the formula, right? We used earlier. So if you have a x tilde f is nothing but x tilde t and e to the power minus j, right? Which is actually this equation. So here we say minus infinity to plus infinity. What is x tilde t? X tilde t. What is x tilde t here? X tilde t is nothing but this equation, right? This equation. Nothing but xt, which is a message signal, multiplied by the complex sinusoid, right? This one. E to the power j twice pi ft. So this one is actually this one, right? So then we have this part. It's actually e to the power minus j twice pi ft. Okay, fc remains here, right? dt. So what we can write? Can write minus infinity to infinity xt e to the power minus j 2 pi f. So I'm using this term earlier, f minus fc t dt. We are just here modified this it to exponential. Okay, so you can see that this portion is here, this part. What is this? F minus fc. So a time domain signal having a complex sinusoids. So a time domain signal having a complex sinusoid. You say if you have a time domain signal with a complex sinusoids, gives you what? Gives you a, this part gives you what? See this part, a time domain signal. You see a time domain signal having a complex sinusoid also have a negative sign here. This actually gives you a Fourier transform of that time domain signal, right? So this is actually nothing but the Fourier transform. This is nothing but the Fourier transform of this signal. So it will be nothing but the x, instead of f, it will be f minus fc, f minus fc, because of this portion, right? So we can write that, okay, what is x tilde f is nothing but x of f minus fc. What is this xf here? In case this is actually Fourier x tilde, this is actually Fourier transform of the modulated signal, right? Of modulated signal. X tilde, right? X tilde. This is actually modulated signal in time domain. So when we Fourier transform, it becomes capital X tilde f, which is actually this one. So it's actually modulated signal, but it's the Fourier transform. Okay. And what is this one? This part is what? It's actually Fourier transform of xf. So it's actually Fourier transform of xf. Xf is a shifted version. So xf shifted by fc. So Fourier transform of modulated signal is nothing but the Fourier transform of xf, or Fourier transform of f shifted by fc. So we can write that modulated or modulation. So we can write that this is modulated signal. So modulation in time is nothing but the shift in frequency by fc, or carrier frequency. So when we modulate something, we actually shift that signal by its carrier. That's actually a modulated signal. That's actually the summary of this example. Now let us give an example of, for example, a typical GSM technology, or GSM, the technology we used for GSM. This is actually our mobile communication, right? GSM means actually global system for mobile. Global system for mobile. In our country, all the mobile companies, they are operated in uh, in GSM technology. There were previously CDMA technology, which is actually abolished. Now there is it is no more there. So let us see what happened in GSM. So for example, in GSM, say this is a baseband signal. Baseband signal means the original signal, the message signal. Okay, which have a width or bandwidth W. So W is equal to 100 kilohertz. This is the message signal, original. So we can say this is a original message spectrum. So this is the original. This is actually a baseband signal. Original message. This is actually the spectrum of the original message. Message spectrum. So we can say spectrum. So original message spectrum, which is a baseband signal. Now, what is the carrier in so it's the frequency is this baseband signal is in centered in 0 with a bandwidth of 100 kilohertz, for example. Now, if you modulate it, what will happen? This will happen, right? So now I'm not in proper scale, but this is like this is our FC. So this will be actually FC plus W. This will be FC minus W. What is the GSM carrier frequency? So the carrier frequency is GSM FC is either 900 megahertz, or 1800 megahertz actually, 1800 megahertz. Here the bandwidth of this message signal is 100 kilohertz. So 100 kilohertz, the message signal is much lower than the carrier frequency. So what happened? You can see here, this is actually the same message signal, only shifted to FC carrier, right? So that's why it becomes FC plus W and FC minus W. It's shifted. So carrier shift the message signal to its higher frequencies. So here this FC is much higher than the W, which is actually, now you see the so this is the carrier frequency is FC. Carrier frequency is which megahertz means 10 to the power 6, and so it's only 9 in gigahertz frequency, and this one is 100 kilohertz, so 10 to the power 3 and 4 5 to 5. So this is the message signal, this is actually in the carrier signal. You see the difference? So what the carrier do, carrier actually shifted this frequency to here, shifted this one to here, to its higher frequencies that the modulation do. Okay.